Oh, we need to do too many things to do the hybrid class. Okay. Yeah, so welcome to lecture 23. I briefly recall we talked about the maximization facet of submodularity and kind of motivated all of these. We spent a bit of time on the representation part. Okay, now problem is not annotating, so I'll have to start this again. Oh, when I do a screen share, it doesn't. Yeah, I think everyone should just try and come to the class. So somehow when I do a screen share, the annotation stops. No idea why. What is 26? Or 23. Okay. Yeah. I was saying that we spent a bit of time on the representation function trying to prove that one specific version, which is facility location, is submodular. I'll motivate the others a little bit more, but I gave an overview of all of these, right? Diversity, coverage, information, representation. So representation function, we have three. Facility location, which we tried to prove it's submodular and there was a homework problem. Did you try attempting it? It'd be really helpful for your assignment as well. So this was your homework problem to prove that it's submodular. I gave you an idea of what saturated coverage does vis-a-vis facility location. Facility location just tries to find the closest point, closest match J to every point I in V, right? Whereas saturated coverage says, well, every point I in V might land up, there's a contribution, right? For every for a J point J in X, you would have contribution from every point I in V. So a potential centroid point J in X has contribution from every point I in the ground set. That's what happens with saturated coverage, but that contribution is kind of limited up to alpha. Okay, so you don't want the contribution to exceed alpha, but saturating alpha. That's only difference. Whereas facility location, you would have a potential centroid point J being or K in this case, right? You look at basically only those points which are closest to it. Okay, that this distinction will be helpful to keep note. So we'll move this here. So what happens here is a potential centroid point K in X has contribution from closest points, right? But there's no saturating required because it's just the closest points. Is this clear that this was a difference? I explained graph cut, but again a reminder what graph cut will do is so following on saturated coverage, unlike facility location which does a max, what graph cut does is it looks at some kind of self similarity between the points in the selected subset X, discounts that from cross similarity. Okay, so that's I think a simple enough message. Otherwise, you can revisit the recording of last week, of last class. So subtract some weighted self similarity of points in the selected subset X. Okay, X is always a selected subset. Just kind of wire that in your heads, right? Next, from cross similarity between X and V. Just the only point is X is a subset of V. So therefore, the weight alpha is going to matter. If you make sure that not alpha, lambda. If lambda is 1, then you're basically just subtracting the self similarity from the cross similarity. Okay, so just remember that X is a subset of V. Fine. So with this kind of recap, we also note that representation functions may not represent outliers. And we did have a discussion. Outliers is a little relative thing. Outliers dropped. So the ones in red square, they are the ones picked. Right? So there's one representation you can see from each of these major clusters. Outlier is basically a minor cluster. So, so you can call them minor clusters or outliers are dropped. Is this clear? Okay. So one point we noted with respect to graph cut itself is that it is it's submodular but not monotone submodular. It's when lambda is less than 2. Okay. So monotonicity is compromised. Yeah, so this is again the same thing now with more examples, but yeah, as you can see in this graph cut, with lambda is with varying proportions of lambda, you're trying to pull the representative cluster to within the diverse set of points or maybe away from them. So the idea is the points within the whole idea is, do you want the point set X to be diverse or not? Right? So if you have a low value of lambda, then you're basically saying that the second point, which is given more weightage, you want that to be diverse. So smaller the lambda, greater is the stress on diversity within X. Okay, with that, let's look at the homework proof. Prove that this particular, oh, what happened? Yeah, so we want to prove that this facility location has some interesting property in terms of submodularity. So let's look at this function. The fact that it is monotone is somewhat obvious, right? Why is it obvious that it's monotone? I mean, as I grow the set X, what would happen?
X is larger than negative S will be greater because points which are farther away from maybe some
Previous point.
then it will be more.
Right. So, let's turn on my camera. Yeah. It's a good point brought out. So as the set grows, as the set X grows, every point every point I in V has more points to choose from. So the max can only grow. Right? K in V sorry, I in V has more points to check for its similarity and pick from as most similar. It's only growing. So therefore, there's no reason why it should shrink. Right? The similarity max value will only increase. Each max similarity will increase, and so will the sum. So good. So very often, the simple reasoning, textual reasoning works out. Okay, so try writing. That's why I'm writing in the class. So you can also try writing. Okay, so this helps, right? Now let's look at. Is this clear? Any questions on this? So with that, let's look at completing the proof. This was a homework problem. So what we did was, we said the conditional gain is f of v given a is f of a union given as f of a, right? And so in terms of diminishing gains, diminishing returns, if you have a subset of b subset of v, then f of a, v given a should be greater than or equal to f of v given b. So this was hint one, or this kind of inequality you could try and arrive. And the second hint I had provided was that you could look at fx itself as a decomposition over the GIs. We have already seen properties of submodularity. Non-negative weighted sums of submodular functions are also submodular. So we said, why deal with the entire thing? Why not look at GI for the ith point in V? What is the most similar point in the set X? Okay. So this was my hint 2. Anyone was able to use these two to prove? It's not very difficult from these two. Can I show that GI has diminishing gains? Did anyone try? Okay. Anyone on the call? Okay, so let's actually write down GI of V given X. Okay, that's the exact expression we are seeking. GI of V given X. Okay, just note the 1 or 2 critical steps. It is K. Now what we have done is we have added V to X. So max of K in X union V of SIK minus max of K in X of SIK. Right? That's just write down. I mean, that's it. You're pretty much there, except that now I can now further think of some simplification of one of these components. So now I'll just again, like I decompose f into GIs. Now within GI, given GI of V given X, I'm going to look at a subcomponent. What is that subcomponent? It is this component, max of K in X union V of SIK. What is that? I've added a new element. Well, it turns out that this component is nothing but the max of 2 different components, right? So the first is the one inside. Yeah, I'm just going to use some color coding here. So this component, which is exactly what you have actually on the right hand side. Just note, make these observations. Max of K in X of SIK, comma SIV, and the max of these two. I added a new element, the max of x comma y comma z is the max of x comma y, right? And the max of x comma y, sorry, the max of x, max of x comma y and max of z. That's it. That's all we are done. Max of x comma y or a comma b comma c is max of a comma b comma c. That's it. Okay. So yeah, more specifically, the pink part has been included using this. Okay. So what next? Now, when I add this yellow part here, the yellow is max of k in x of sik. I can do something smarter. I can just say that, well, I have the same component here and here, and I'm subtracting the second component from the first one, right? Max of, I can write down again in simple terms. What we are doing here is max of a comma b, right? Minus c, minus a is what? Max of 0 comma b minus a. Is this clear? This is the result we are using. Is this result clear? Max of a comma b minus a is max of 0 comma b minus a, where our a is this term, b is this term, this is nothing but b minus a. Okay, so then if x is subset of y, then now I'm growing the set. Okay? Earlier I had just an x. Now suppose I grow this x to a set y, made it darker green. Okay, what happens? So I'm looking at now max of, so just this part, the final component is all I'm focused on right now. This part I'm now going to expand the x to y. Same component, same thing, same concept. Now I have y instead of x. And now you can easily see that this is less than or equal to max of 0 comma siv minus max of x in k in x. Now I have, I mean, if the second component, I just have fewer elements to do a max over, then it will be less negative. Right? This component, the second component will become less negative. Or cannot be more negative. That's stop saying less, cannot be more negative, since x is a subset of y. Okay, so let me know if you have questions. This is pretty much there. Any questions? We're really talking about this. Second. Okay, so basically GIX is submodular, showing this diminishing returns, and submodularity is closed under non-negative linear combination. The sum will also be submodular. Got a flavor of how we can prove. We'll do one more proof, entropy, but we'll give hints for the others. Just give intuitions. Okay, if there are questions asked, otherwise we'll move to the next step, next set, diversity functions. Now, what are diversity functions going to capture? Going to look at how spread out the points are, right? And how spread out the points are with respect to their similarity kernel. And the subset is S, right? Subset of points S are with respect to similarity kernel L. Okay, there's an overall similarity kernel which measures how similar every set of points is to every other set of points. That's a L, this entire matrix. Okay. So L you could think of as xi transpose xj, or Lij is extra xi transpose xj. Okay, let me. This is Lij. Now what I'm going to do is I'll take a subset of points S from Lij and only compute the log of the determinant of that subset. Okay, so let's say I had this massive matrix and I'm going to say I'll subset my points S. Subset would correspond possibly to a bunch of these rows and columns. Let's say this row and this column. So now I'll have, let's say these are 2 points, right? So I'll just pick up basically these 2 points. So LS will be just these two, right? Let's call it SPQ. Oh, sorry, this is SPP, SQQ, SPQ, and SQP. These are just 2 points. Okay, so it'll be SPP, SQQ, SPQ, SQP, assuming that these are the 2 points, P and Q. I made a mistake. I think it's okay. I mean, it's okay. They are similar. The similarities are supposed to be symmetric, so I should have written this as SQP ideally, but it's okay. So you'll have something like this. This is when S is just P comma Q. So you'll take a subset and determine the log of the determinant. What is this capturing? I mean, you know that determinant has something to do with polyhedrons, huh? Volume. The volume, right? So volume determinant will represent the volume. Should capture the volume of some kind of a hull, right? Some kind of a Titus encompassing polyhedron. So I would say roughly. Okay, it's in fact there's some proportionality constant, etc. That's why I call it roughly. Okay, so this is the basic idea. More spread out the points are, the more the volume, not necessary. Yes, the more the volume. I'm asking you this question. Is the volume going to increase with the number of points? Is the volume going to increase with the spread of the points? Is there diminishing returns as I keep adding a new point? If I add a new point to a subset or as against a superset, okay, so let me go to the next slide. Okay, sorry, I was trying to show this similarity. So let's say you have these 3 points, these points, right? Now let's say I add a new point here. This is point number 1, or maybe here, point number 1. Okay, but now suppose I add another point, point number 2 here. So with point number 2 lead to higher increase in volume when you had point number 1 or when you didn't have point number 1. let me ask this in text, right? Would point 2 yield higher increase in volume without point 1 or after insertion of point 1? Any thoughts? Yes, any answer? After insertion of point 1? Sorry, you don't think either can be made? The other set of points are the same. So there is already some spread. I have added one more point. It has probably increased spread, but the point 2, when would it have seen its more value? When with the original set of points, if I add this new point here, as against after increasing the set. Before, right? Right. Answer is before adding, before inserting 1. This is diminishing returns. If at all, right? If at all. I mean, it may not, there may be no, it may be equality. It may add no additional, no, I mean, no higher value, but it cannot diminish. I'm sorry, it cannot increase. The returns cannot increase as you add these new points. Okay, so with this, one thing seems to be clear, that we are dealing with submodularity again. Okay. Okay, so all this implies submodularity. That log det should be submodular. In general, diversity functions need not be submodular. Okay, but log det is indeed submodular. Do you think it's monotone? Do you think it will increase every time I add a new point? So that's a little tricky. I don't think intuition is good enough there. You'll have to write down expressions. So it will increase.
After adding a point, the spread will be increased or it can get the constant.
Okay, so it turns out that it is not monotone. It's submodular, but it is not monotone. Okay, so yeah, I mean the intuition says that as you add a new point, right? I mean volume wise will it shrink. So that's where you have to actually write down the expression. It's, as I said, it's proportional, but then proportionality can get affected.
This is a multipolarity set, not the original point.
Right. That's a good point. So it's a volume of the similarity matrix. Volume as per the similarity matrix. Yeah, but there's also a proportionality aspect. Okay, so overall, it is not monotone. And it turns out that log det is on probably the only diversity function we'll see, which is even submodular. There are other functions which are not even submodular. And good thing, of course, here is that log det has picked up an outlier. Because it's trying to pick diverse points, it has picked up outlier. That log det has picked up outlier. And that is typically expected of diversity functions. Okay, and look at one interesting thing. Logdet is not a function of the original set V. It's only a function of the subset. Facility location, graph cut, we had a V, right? In graph cut, in logdet, it's only a function of the selected subset. So unlike representation functions, okay, it'll be good if you also kind of bring out observations as you proceed. Okay, so this is what I was talking about. If you have, you can actually come up with a probability distribution. P of y being a subset S is proportional to the determinant of the this matrix LS. And that's basically the volume of all the xi's in the similarity space. Okay. And this is submodel. And for reasons we already see. So you can actually define this similarity matrix and compute the similarity. Now, what you see on the right-hand side is point sampled with respect to a determinantal point process. So imagine that you are sampling points with respect to this distribution. P of y equals S is proportional to blah, 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 right? As against uniform, right? So these are points sampled as per logdet distribution. And you see that, you know, even when you're sampling points, the points are well spread out, right? As against uniform, where you will find, you know, too many points are clustered at certain locations. So it's a bit uneasy, right? You have too many points here. You don't find any such localization of the points selected in the case of DPP. Is this okay? Can I ask questions here? There are other diversity functions. Yeah, sorry.
The first step itself. Why can't we use any static features? It can be a name or something like that.
So the exercise can be any features.
So maybe we can also see like probability of selecting the y equals to S can be volume of that X in that features. Defining volume in those features. Why are we calculating the similarity score? What's the motivation of that?
Similarity score is either, most of these will either look at point-wise similarities or point-wise diversities. Because ultimately you want to identify points, right? You're doing discrete optimization. So most of these will not characterize the entire space. But if your question is, are there functions which actually look at the original space itself, right? Like k-means. The issue with such functions like k-means is that you may get a cluster with a centroid which is in no man's land. Here we are trying to find a cluster which coincide, a cluster with centroids which coincide with one or more of the points. Is that clear? Yeah, it's a good question. So here are a couple of others. You can also come up with dispersion functions. So what's a dispersion function? Here you're looking not at similarity but distances. I mean, coming back to what you're asking, that distance is also some kind, maybe Euclidean distance. So it's still a pairwise computations that the entire clustering boils down to, or the diversity function boils down to. So you're looking at distance dij between elements I and j. Now let's look at what each of these does. Dispersion min sum says I'm going to look at again only within X. Okay, there's note that none of these involve the ground set. None of these involve the ground set exactly like the DPP, right? So I'll just copy this entire sentence. Okay, so the same observation. Of course, the notation has changed here. All these, just make slight change. Are a function only of the selected subset X. Just note that down. Modulo that, what is this doing? It's saying for every point in X, a point K in X, I look at the closest point L in X, right? And I want to overall maximize this this entire closest distance, right? So in words, what are we saying? It's saying that we want to maximize the sum of smallest distances for from each point K to some point L, both in X. Is this clear? That's the first one. That's dispersion min sum. What is dispersion min doing? Actually, yeah, let's write down the second one. If we want to maximize not the sum, now in the second case, maximize the min of all pairwise distances in X. Okay, that's the second one. Is this clear? The difference between the two? Because you're dealing with maximization, so just remember that semantics. Right? I hope you could get the difference between the first and second. And the third function, it says, well, I want to maximize. We want to maximize the sum of all pairwise systems. That's it. Dispersion sum. Okay, so for obvious reasons, none of them we would not expect them to be actually monotone. None of them would be monotone. However, there's been the left hand the dispersion min sum. Okay, so there's some result that shows that is submodel. I'll give a reference to that. I mean, it's been claimed to be submodular. You can basically look at that for correctness. Okay, so this is the dispersion min sum. In case you're interested, it has been proved to be claimed to be submodular in this WACV paper 2015. Okay. Any questions? Otherwise, we'll move on. Okay, and yeah, the differences, as I said, it's pairwise sum, pairwise min, or sum over min. That's the difference. And in all these cases, you'll find that the outliers would be often represented. The last is coverage functions. So what we do in coverage functions is we have certain concepts. Instead of representing other examples, we are now talking about representing words, representing concepts, representing objects. So representation functions were about representing other examples, right? coverage functions are about covering objects or features Okay, so let's understand this a bit better. So you have these features here: dog, cat, bird, etc., etc. And what we are trying to do is select instances which cover as many concepts as possible. Set cover you have done. Have you done set cover in any of your basic courses, UG, PG? So what is CI? CI is the concepts covered by instance I. So let's, with respect to the example, let's look at the first one, right? C1. What is C1? Is the concepts covered by the example one, which is cat, bird, and beach. That's C1. Likewise, you can write down the C1, C2, C3, etc. Now, as I take a union over all the CIs, some of these objects will be covered by multiple I's. So, for example, bird is also covered by C3. So C3 has covered bird. It has covered, I don't know, some other instance. Okay, so it is covered. So now if you look at the union, obviously there's some redundancy, and that's again why we get some kind of submodular property. I mean, see, the thing is, even submodularity is attractive, but some functions look like submodular functions also, right? Like the diversity functions, there's some diminishing returns you expect, but may not be strictly adhered to. So often we intuitively define some functions, and they seem to have diminishing returns. They seem to be very useful for the application. And then we look at it in retrospect. Is it really submodular? So set cover could be another function like that. But let's see if it's submodular. Okay, so now you see, as you keep adding more and more instances, the same set of objects will keep getting covered. No new objects will get covered. Correct? Expect that as we keep adding instances, the set of objects being covered would keep repeating. Okay, so therefore we expect some diminishing returns. Okay. In addition, we can also assign weights to concepts. Okay, so here again, I can say that the male is there. There's all these are concepts: male, car, greenery, beach, water, mall, female, etc. Now, it could be that certain concepts are more important than certain other concepts, right? So, if I'm dealing with traffic, then greenery is not important; it's just background, right? If we are dealing with traffic video analysis or image analysis, greenery will be background and have less weightage. Okay, so that weightage is like W or WA associated with the 8th concept. Okay, so that's the other aspect here, WA. So each concept can have a weight. Now, I have in the left-hand side, I've just said W, but the W is a modular function. I mean, once you decide what are the objects covered, you can just say, okay, this W of set of objects covered is sum of sum over all the objects of W of the object. Okay. So it's a modular function. Sorry, this is not visible properly. Let's make it black. I hope this is clear. Okay, so W is just, I don't think we need to bother with W too much. It's just a way you can add. It's like repeating that object as many times. You can say car 1, car 2, if car is so important. So, okay, so I'm giving another example here. This is, from our, I think, this is my student Ramkrishna Berry in ACL 2015. I think you've seen this work. So imagine you're trying to cover documents, and you're trying to cover documents through Wikipedia concepts. So all you see, all those concepts you see here are Wikipedia concepts, okay? And you're trying to cover the documents. Now, obviously, as I add more and more concepts, like technology is covering some topics, plants cover some topics, companies cover some topics. You can see this, right? Places. But if I keep adding concepts beyond the threshold, we are not going to cover new topics. That's also because there's a hierarchy. There's some subsumption relation. X covers Y, which covers Z, and so on. Right? The same instance may be covered by multiple nodes. So things become even more interesting when you have hierarchies instead of just flat structure of coverage, right? So notion of coverage, if it's big, is through a hierarchy. Okay, that's what we see here. Okay, so yeah, I mean, we can see this. Some of these have fine-grained topics. Apple band. You must have seen Wikipedia disambiguation pages, which creates these clusters of topics. Okay, so some are fine-grained. You can see on the right-hand side. There's a disambiguation page for technology, for Apple. Sorry, Apple, which says okay, Apple has some aspects of technology, some aspect of plants, some aspects of companies. So each of these is a concept being covered. But it's a hierarchy of concepts being covered. You can see nodes on the hierarchy being covered. Okay. Here's I mean, you can actually convince yourself that this is submodular, right? Sorry, this is 4, this is 5. I hope you can see the numbers. Okay, so, and the documents are 1, 2, 3, 4, 5, 6. And you can convince yourself that the function is indeed submodular, right? If you are going to, I mean, here in this case, what we have shown is, okay, documents, instead of trying to cover these 4, if I try to cover 6, well, you can actually find 2 different concepts, 2 different sets of concepts, which have very different coverages. So this is a, of course, submodular maximization problem. Submodular maximization is about identifying, say, 2 concepts which cover all the documents, right? On the RHS, 4 and 7 cover all 6 documents, right? Whereas on LHS, the 4 and 5 cover only 4 documents. That's a maximization problem. So why is set cover submodular? Okay, I'm not going to go to the proof, but the no, you can have like you can have discrete case. This is what you have shown below is discrete. But you could also think of set cover in a continuous case. So what's the continuous case? I'm trying to say fix some sensors, right? And I want to maximize the area covered. 5 sensors. Where do I say fit it? Now, let's take look at the continuous case. If A is a subset of B, now the simplest case is when A is a subset of B, and the new point V, the new sensor, right? Whose area? Okay, think of these as think of these each of these as circular filaments of sensors, right? Think of each disk as a disk of influence of some sensor, right? So LHS, what we have is V covers disk disjoint from the coverage of existing sensors, right? Now it's very easy to see the gain that you get therefore in the left hand side is it's a complete V, complete F of V. Whereas now after you added a lot more, you just some small area to boast about. So it's obvious. I mean, I don't think we need to spend time doing this, but in case you want to do it, the discrete case I've given some hint. Again, I'll leave it to you to complete it. Okay. If you take the simplest case of W being size cardinality, then if X is subset of Y, we can basically write down, right, W of very much like we did for facility location, and you can show that in fact the inequality holds. So proof is not very difficult. So try completing arguments of this proof. I would like to move on to the information function class, which is very critical for us. Okay, so I leave it at this. I'm sorry. Any questions at high level? So interestingly, you can not just do weighted, but you can also do probabilistic coverage. So you can allow for how much is a greenery there or a male there in the car, right? So that's the notion of probabilistic. So you can say that certain edge weights, for example, here the male is very obvious. The male is very obvious here, but there is male is male is very obvious, uh, somewhat obvious here, but even more obvious here. I made a thicker edge, right? Likewise, there's a male very obviously here, but there could be images where beach, for example, beach is a lot more obvious here than it is say here, right? The edge weights are denoting the extent of coverage, so probability of covering concepts. And let's say that probability that image I covers concept J, or it could be probability that that document I covers concept J. Right? I mean, you could some of the concepts could be stop words, so you may have low probability, like the, a, and so on. Or sometimes terms can be ambiguous. Manned aircraft versus a man on the aircraft. Right? So man you can't see, but it's manned. Probably because it's not crashed so far, right? So, whereas some man on the aircraft is very more explicit. So 1 minus Pij, right, for a fixed I is denoting the probability that concept J is not covered in example I. A product over all these concepts, right? I is basically saying that None of these examples are covered concept J, right? This entire thing is probability that none of the examples have covered concept J. And 1 minus the whole thing is basically saying, oh, what's the probability that at least one of the examples covered concept J? It's very obvious, right? So I think this whole thing is basically example covered concept J. So this is a very, if you've done a graphical models course, then you'll find this noisy OR. It's like a noisy OR. It is also called. Okay. So you can have this. This again turns out to be submodular. Now you can get fancier. You can say, oh, why discover features at one layer? Right? Think of deep networks. So you could think of layer 7, but layer 7 is a composition of all the previous layers. I mean, we're talking about forward propagation, not backward, right? So you can think of this forward propagation, and you can see that the coverage of this layer 7 on a set of examples instances is through a G function, a composition function. What did we know about concave functions? Concave over modular. If the G's are concave, what do we know? If G's are concave and M is modular, non-negative modular. Like, square root of the size, as we took that example. Then what do we know? What did we see? The composition is composition. Okay. So now you can actually again make use of all these interesting properties to come up with more, I would say, more realistic cases when you have deep networks. How do you come up with notions of coverage? Okay. So yeah, I just drew this to show that you're talking about summation over U, and this entire thing is this G of. Okay, so this, yeah, you can have nested feature-based functions. The ground set, you have V0, V1, V2. The ground set is itself kind of changing, right? But even in such settings, you could talk about some modularity through of the composition through nesting. Okay, we'll not get into the details further now. Now, importance terms, right? If I showed you this DAG about selecting Wikipedia concepts, some concepts like in a thing, everything is a thing, right? Saying that Apple is a thing is not informative. So importance functions say, well, how generally the instance is important or the concept is important. We saw, for example, the summation over all the concept weights. That's a modular function. So importance terms are typically modular functions. How important is an individual concept? For example, I mean, you can give more example like e.g. if you consider TF IDF, if you have words, TF IDF is a function of that particular word. Term frequency, inverse document frequency, right? Or frequency itself, prior probability. For example, depth of a concept in a DAG. I gave you that example of DAG, right? How deep is it? Or maybe a square root of or 1 upon that depth. Depends on what you want. So if you're looking at these, right, how likely is that this object is there in this image? So these scorers, all of these could be importance functions. Now information functions. We're going to spend a little bit more time on this now. Information functions, if you have discrete random variables x1 to xn, the joint entropy of the variables indexed by a subset S. Okay, this is a subset. The subset could include x1, xn, only maybe it may not include xn, right? It may include some other points. This joint entropy, what is its property? Okay. So it turns out that this joint entropy, if you have discrete random variables, it is submodular. So this slide has many things. We'll actually go have more sparser slides. Okay, so this entropy function, entropy is a measure of uncertainty. You can have a joint measure of uncertainty across multiple random variables with a joint distribution. This entropy is submodular. Okay, and we'll try and prove that. We'll prove that. Okay, proof in next few slides. On next few slides. But there are some other interesting things which I've also highlighted. Why are we talking about it? Well, not just why are we spending a little bit more time on it? Not just because it's submodular, but there are some other functions around it. Okay, so I mean, for example, we will prove that this inequality we'll prove f of a union e minus f of a is greater than equal to f of b union e minus f of b if a is a subset of b. That we'll do that. But there is another interesting thing. If you look at a union e minus a, h of x, the entropy of h indexed by a union e minus entropy of x indexed by a, this is the conditional gain. We have given it a name, right? Called it conditional gain. Okay, so recall. Okay, so this conditional gain, we'll see some interesting properties of conditional gain per se as well. In fact, we'll see a bunch of properties not only of conditional gain, but of also called information gain, also of mutual information. So entropy is interesting also because it has many of these derivatives. Let's define a bunch of them. Okay, so this proof I'm going to do this proof, and in that process I will actually have a whole bunch of other definitions. Okay, this is the proof we'll do on the next slide. Okay, so let's look at discrete entropy. I'm going to define some terms. If you can write down, that'll be great. Okay, just write down some of these terms. So conditional entropy. The first term is called conditional entropy. And that proof is very simple. Just write down definitions, you will get it more or less. And interestingly, the proof involves concavity. Okay, so concavity it's a ghost that's going to haunt you. No matter where you go, convexity and concavity will follow you. So the first term, conditional entropy. What is it? H of y given x is some more all values that x can take of entropy of y for that fixed value of x into the probability of x. Basically, the expectation. So you can write this, and I'll just give you some other names for this. Right? This you can also call this the entire thing as expectation of h of y given x with respect to the distribution of x, okay, p of x. When you write expectations, you should know, you should write respect to what distribution. So as you write down did you write down first expression? Will unfold in parts. So it turns out that just by some algebraic manipulation, h of x comma y, the joint entropy is h of x plus h of y given x. This follows from simple algebra. which we will not prove right now. Okay, I'm assuming you can write down that. Okay, some simple algebra. So even those of the call, please take some time to write this down. Have you written the first part, first line? Yes. Give me a heads up. So the second line is called mutual information. It's defining mutual information. What is it doing? It's saying, well, let me look at the joint distribution of x and y. That's there. But from that, I'm going to remove the independence of x and y. So P of x comma y is like how well they're correlated, right? The joint distribution. But this division you must have seen, likelihood ratio. If you've done a simple, you've done probably BTech students would have done this 215, right? CS 215. So did you have this independence test? How independent are x and y, right? If P of x comma y is equal to P of x into P of y, then x and y are independent. So this is like saying how not independent they are, right? How much is the information between mutual information between them? Okay, so these are the notes. Roughly captures. Yeah. These additional comments you don't have to write. Just write down the main expression. That's good. Okay. So once you have this expression, again, through simple algebra, again, like earlier, we will say this I of x comma y, mutual information, is entropy of x minus entropy of x given y. To remove the, I want to capture the mutual information, right? So I'm saying, okay, from x, I remove things that are redundantly known with respect to y. Or I could, from entropy hy, I can subtract the conditional entropy of y given x. Both are equivalent. Again, from simple algebra, which is not worth going into the class. This is the second step. The third step, again, something you would have probably, can I move to the third? The third is the Kullback-Leibler distance between two probability mass functions. And how far away are x, distribution on x and distribution on y. So it's called d p distance from q. And what is it doing? It's asymmetric. Okay, it's an asymmetric measure of distance. So probability between two probability mass functions. As asymmetric because it's saying p of x into log of px divided by py. So this is basically expectation. Think of it as expectation, same as expectation with respect to the distribution p, distribution of p of px divided by qx. Sorry, log of px can also take a difference as log of qx. That's another way of writing it. Okay, now an important inequality related to the KL divergence. It's called Kullback-Leibler or KL divergence. So if P and Q are such that the distance between P and Q is equal to 0, then it must be that P must be the same as Q at every point. If the distance, if the P is the same as Q at every point, then distance must be 0. That is KL divergence rather, not distance. KL divergence must be 0. At all other times, D is greater than or equal to 0. It can never be negative. Okay. I mean, intuitively, what all we're saying is KL divergence. It may not be symmetric. While KL divergence is not symmetric, it collapses to 0 if and only if the 2 points are the same. And in this sense, it's much like other distances. So, like therefore, there's a name. Therefore it's called divergent. Right? At least there's something intuitive about it. Okay, so the next slide, what I'll do is quickly prove why this holds. Right. Next slide, we'll just prove this. And this proof is critical. On the next slide, we prove it because this is important for submodular, proving that the entropy is submodular. Okay. So here we go. We continue with information inequality. So now this you don't have to write. This you don't have to write. This proof is intuitive, but just a little bit. So I'll run through this. If S is a sub, if I consider only those points in X where Px is strictly greater than 0. Obviously, if I'm going to divide by P, I should be careful. Okay. So the reason that we get this inequality holding is as follows. So the reason for this inequality with equality if and only if Px is Qx is now if you consider negative of B divergence. Okay. I think this should have been X. Sorry. Take some more. Something is X. This should have been X. Yeah. So roughly what we are saying is I think in one place is showing X. Okay, anyways, I mean, let's just consider the support set. So consider the summation. Now what I do in this step is I take the negative term inside minus into the log. That will basically flip the fraction. Right? That's the first step. Now this step is important. What we are saying here is that log is a strictly concave function. Okay, how does log behave? Log is a strictly concave function. How does it behave? This is how log behaves, right? So that's what causes this particular inequality. this behavior, the concave behavior. Okay. So what is the strict concavity of log doing? It's saying that this P, which is so this Px is a convex combination, right? This Px sitting outside is a convex combination. So instead of, so think of these as in alpha, the theta i's, right? With sum to 1. So theta i's such that the theta i's, theta i's sum to 1. So I'm just taking advantage of this property. I'm bringing, so instead of saying that summation of theta I of f, right? This is, let me write this expression down. You have a summation over I of theta I f xi. I know that this is less than equal to f of summation of theta I xi for concave f. We know that. Is this correct? Is this correct? Yes. Oh, sorry, I made a mistake here. I should write this as summation over I. Summation over I theta I x. Okay, so all we have done is just let me put that this here as well, just so that. So all I've done is I've taken the log outside and the theta is inside. This f, think of this f as the log. Okay, so that's it. So therefore, with that inequality, now the rest is very simple. If you bring now px into qx by px, what happens? Px and px cancel out. The summation of the log of qx or the support set. Now this is less than equal to the log of qx. Now we were only considering x such that px was non-negative. But on all the other points in x, qx would might be non-negative, right? So therefore, this inequality, the last step, this inequality, okay, since qx would be 0, even for all the x that are not or are not in S, right? That's a support set S. So when I now add back all the points and have less than equal to, which is a log of summation of qx is basically 1, the log of 1, which is 0. So basically, you have proved that the negative of the KL divergence is less than equal to 0. Is that clear? Now, since further log is strictly concave function that we saw earlier, it's not just concave, it's strictly concave. We have equality, know that this equality holds if and only if basically the qx by px is 1 everywhere. That is px, that all these points must be the same. Basically. Strictly concave means the equality holds if the points are the same. Okay, so strict concavity requires all the points to coincide. Okay, let me write down here properly. Strict concavity requires that equality holds if and only if the arguments coincide. Right? So that's px is equal to qx. Now let's just quickly just conclude this. So what is I? I is the mutual information, and I can be written also slightly differently. I is the same, IXY is the same as the KL divergence between Px comma y. So there's this inside bracket, there's a x, P of x comma y from the distance between Px comma y and the independent distribution Px into Py. This is exactly KL divergence. This is exactly mutual information. Okay, so I of x comma y is the KL divergence of these two. You can convince yourself, right? Because mutual information looking how much is the information as against the independence. KL divergence is doing the same thing. Measuring how much is the information as against the independence. Okay, so with that, now this means that equality holds if only Pxy equal to P of x into P of y. That basically at every point. That is x and y are independent. Okay, so with this all ammunition, we have the final result that Ixy will therefore be equal to 0. This is the final result. Ixy is equal to 0 with equality if and only if x and y are independent. But what is Ixy? We already saw the relation for Ixy. If you remember the one in blue I wrote. No, sorry, one in red I wrote. Ixy is hx minus hx given y, right? This is the equality we had earlier. Ixy is hx minus hx given y. So therefore, hx given y is less than or equal to hfx. You see this? That's the most interesting part. That now I have got the conditional gain on the entropy is diminishing, right? Entropy has diminishing. Okay. I mean, you can prove this. I've not completed it, so I would suggest that complete the proof. This is okay. So we are there. This is actually going to be the homework for you. Okay. We are almost there. I'll leave you with this homework problem. We'll meet on Monday. Please do attend this homework problem. This again, as I said, each such homework problem gives you expands your the gamut of tools that you get exposed to for your assignment as well. Thanks.